Hello and welcome to today's video, where we will show how we pair Optimi and Simulate. We will quickly highlight the capabilities and differences between Minitab's internal optimizer and Optimi's AI-driven optimizer. As a common and accessible sample, we will use Simulate's own optimization example as provided on their website to demonstrate the differences and improvements Optimi can bring. In this scenario, we model the processes for a cafe. There are several simple parameters that managers of any cafe can control, but at the same time, there are many uncertainties they cannot. The controllable parameters of this cafe setup is what we will optimize, so we can manage uncertainty while maximizing profit. The controllable parameters are the number of baristas, chefs, and servers that we can hire on a given day. And the uncertain parameters are the number of people entering the cafe. For simplicity, we will keep all the predefined restrictions from the original scenario the same, so we can easily see the improved optimization Optimi can bring. Firstly, let's see what OptiQuest does. We're going to optimize the profit and the number of people processed in our cafe. Next, we see the parameters we want to optimize, the baristas, chefs, and the number of servers, as we'll do in both scenarios. The advantage of OptiQuest is it's very simple and straightforward, going to the point dialogue. Once we start the optimization, either focusing on the number of trials or how long we want to run the optimization for. While there is a built-in calculator to give you some clue about the optimum, it is quite intransparent for the user what this should be. One other advantage of this system is that you can right away see the current optimum that one can set in their process. But essentially that's it. You just simply get some optimal points without too much explanation about how to optimize the rest of the process or which parameters influence what and in which direction, whether in the positive or negative. And if you cannot make just discrete steps, what are the insights that you can have for your own process? Now let's bring in Optimi. We will jump to the most value-added part, the automation and linking of Minitab's Simulate software to our AI optimization engine. Using Simulate's own Python and COM bindings definition, we created a script to pair the two softwares together. This short script you see on the screen was written within 1 day, and half of it is actually from Simulate's own online example, and the other half is simply the customization of the 3 parameters we wanted to optimize for. And here's the actual technical linkage between the two softwares. At the top, we see our system feeding Simulate with the 3 parameters we wish to optimize, the actual script that fetches and commands Simulate to perform its calculations, and the 2 outputs that we will optimize for, just like we saw in OptiQuest. Once we hit run, we can see how the software is invoking Simulate to collect all the batches and all the results it needs to perform its own modeling and calculations. Unlike OptiQuest, the system itself figures out how many batches and calculations it needs to build an AI surrogate model. Finally, let's get to step 4 of our industrial AI process, visualizing the results. Output 1 is the profitability, and output 2 is the number of people processed. We can actually look at both of these at the same time so that it's easier for us to compare the sensitivities or any other information and insights at the same time. For example, on the left side, where we see profitability, we see it's actually impacted by all 3 variables. Where in terms of the number of people processed, the significantly dominant variable is baristas. And of course, if we go back to the system settings within the Simulate model, we would recall that baristas have a much lower cooking time than chefs. Then this confirms that because they have such a low cooking time, of course they will be the dominant factor. Insights like these are super valuable for people with complicated processes to actually be able to judge if what they're looking on makes sense or not. If we continue, we can explore all of the functions that Optimi has to offer, including increment functions that basically show us the peak parameter and when its optimum is reached, and whether increasing one variable will have some effect on, for example, here profitability or throughput. In this case, we can see that adding servers actually leads to a negative profitability, which makes sense because for each additional server, we will have to spend a more fixed cost to pay the servers. Next, let's look at function plots, which essentially show us how does the total change in the output with a given parameter. So for example here, we can see that as we increase the number of servers, the overall profitability goes down. Again, because if they're increasing in number doesn't increase throughput, they're essentially adding financial weight onto the system instead of improving it. That's just another one of the pattern insights we can see with all of these visualizations. One of the most useful things, however, is not just looking at each variable independently, but how they interact. For example, we can always see linear growth very easily as people, but once you see interactions, that means how one parameter influences another, then we can truly get insights into how the system is behaving. This means visualizing as one variable goes down, for example, how it's influencing the overall solution. Of course, we could do this even for more variables than just two by combining it into something called a 4D graph. These graphs might look like they'd be a little bit hard to view because of the way that they're arranged, but of course, thanks to visualization techniques, you can zoom into the various little layers and try to get a little bit better of a viewport as these interactions take place. This is all part of the advanced visualizations that Optimi can provide, going between 2D and 3D plots, back and forth with the results. Now let's get to the most powerful feature that we have to offer, which is multidisciplinary optimization. What does it mean, multidisciplinary? Well, exactly like we had multiple objectives, you can have different disciplines that go in their own directions, and you want to optimize them and see where they all cross over. In here, just very quickly, going again for the profit, we see that the profit here peaks in one of its disciplines. That is the number of servers, the number of baristas, and the number of chefs. On the other side, here we see several regions that actually maximize, if we go to the result, that maximize the entire solution. So here we have a region of preference, and here's a second one, and there's a gap. That's where we actually want to avoid being. So in this domain, in this discipline, there are regions of maximum, so to speak. Now, the most interesting thing in terms of multidisciplinary optimization is seeing where these two overlap. So if, for example, you have 3 objectives you want to overlap, 3 disciplines, 4, 10, or for even example, have different CAD tools. This tool, our Optimi software, is able to show which regions you want to maximize on which inputs, which will lead you to the best results. This is what it means to have multidisciplinary optimization capability. So once again, the idea of multidisciplinary optimization is being able to have all of your different domains converge in at least one area that you're maximizing, or if you so care, minimizing, or whatever objective you reach for each domain, and have those overlap. This is the power of multidisciplinary optimization across different domains and different tools. That is what we bring to the table. However, if we just simply wanted to see the optimum for each of the parameters and the outputs, we can go to the regions of minimum and maximum, which in engineering sense tell us usually the best numbers. And even here, we can kind of see the divergence between the two outputs. To maximize profit, we have some combination of servers, baristas, and chefs. However, since most systems in the world are non-linear, they can easily diverge in terms of optimal. Where here, in order to throughput the most amount of people, the solution clearly tells us that we want to take as many servers and as many barista orders as possible in order to maximize the throughput, which is the number of people served, which might not necessarily be our most profitable combination of all parameters. Just showing how difficult optimization can be, even with a relatively simple example like a cafe. Without analyzing everything to death, perhaps it might be insightful to simply compare outputs against each other to see how they're influencing each other. We'll take the optimization of the profit and compare it to the throughput of the entire cafe and see how the two solutions might be against each other. Here we can compare in a 3D nicely looking matrix how the customers and profit segments interact with each other. Of course, we can turn on and off individual parameters to see their actual influence, but we can also manage quite nicely to see where are clusters of good combinations. For example, whether we process 500 customers at a time or the more likely scenarios of processing 900 customers, and how the spread goes very easily into negative, meaning we're not profitable, to a more profitable outcome. Having visualization such as this is really useful as opposed to obtaining a simple optimized point.